Speed of a wave on a string. Now for this lesson, we will use Phet Simulation. I will put the link for this simulation at the description below so you may visit and explore by yourself. So let's familiarize with the simulation, with the feature of this. So you can create mechanical wave manually using this range, or by oscillate, which means we have here, it oscillates by itself, or by pulse, by clicking this button. Okay, it just simply pulse. And you can choose the N, either it's fixed N or a loose one, let's see, or no N. So for you to visualize how periodic waves behave, you use this oscillate. So you can see here, the tension is set on high. So the tension is the force along the string. So if you set the tension at its low, you can see here that it creates a greater frequency and it moves faster compared with the high. Also, the tension influence the frequency of the wave. Damping, which is the decrease in the amplitude of the oscillation, if you set damping at high, so you can see the great decrease in the amplitude. But if the damping is none, if you set it none, so the amplitude does not change up to perpetually. So let's put it in slow motion. Okay. And attention at high. Now, if you adjust the amplitude at zero, it simply does not oscillate or does not create wave. But if we increase it, okay. So that's how it goes. And the frequency, if we decrease the frequency, we can observe it gets lower. But as we increase the frequency, it gets faster and faster. And also, the period decreases. Now, let's see this manual. At zero damping, attention high. So the speed with which the wave moves to the right depends on how quickly one particle of the string is accelerated upward in response to the net pulling force exerted by its adjacent neighbor. So in accordance with the Newton's second law, a stronger net force results in a greater acceleration. Let's see. Oh, and thus it's move faster. Now, if we decrease the net force, then we have a slower acceleration. So the relationship between the velocity and the net force can be described by this formula. V is equal to the square root of F over the mass of the string divided by the length of the string. Therefore, a wave travels faster on a string whose particles have a small mass on a string that has a small mass per unit length. The mass per unit length, which this denominator, is called the linear density of the string. Now, let's solve this example problem. A transverse waves travel on each string of an electric guitar after the string is plucked. The length of each string between its two peaks N is 0.628 meter, and the mass is 0.208 gram for the highest pitch E string, or the number one string, and 3.232 grams for the lowest pitch E string. Each string is under a tension of 226 Newton. Find the speed of the waves on the two strings. Okay, so the speed of wave on a guitar string as expressed by the equation V is equal to square root of F over M over L, depends on the tension F in the string and its linear density. Since the tension is the same for both both strings, the smaller linear density gives rise to greater speeds. So we expect that the wave speed to the greatest on a string with the smallest linear density. Okay, so for the highest high pitch E, the velocity is equal to the square root of force, which is 226 Newton. Oops. Over the mass of 0.208 times 10 raised to negative 3 kilograms over 0.628 meter. Therefore, the velocity is equal to 826 meter per second. Now, for the low pitch E, using the same formula, we're just going to change the value of mass. Instead of 0.208 grams, we use 3.232 grams. Therefore, the velocity is equal to 207 meter per second. So that's how we get or compute for the velocity or speed of a wave along a string. Now let's try this. Test your understanding.